long enough, and we see that the signal gets repeated, so we get the period, and we can construct diagrams like this. This diagram also shows a lot of diversity in terms of stellar multiplicity. So the dots that don't have any border are planets orbiting single stars. And the symbols that have a black border are orbiting binary stars. These are the circle is S-type and P-type. And there's also even a few planets detected in triple star systems. What are these? So there are two types of planets in binaries. We have on one hand the possibility that the planet orbits one of the stellar components, is this S-type that you see here. And we have also the possibility for much closer binaries that the planet is orbiting the two stars, a circumbinary planet or P-type. The S-type and P might sound a bit weird, the nomenclature. That comes just because this planet has a satellite orbit compared to the secondary star, and this one has a planetary orbit relative to the two stars. So that's the way at least I found it useful to remember S and P type. Planets in binaries are very important because actually we don't know so many, but we are starting to know a lot, as this plot depicts. But binary stars are important for exoplanets because half of the stars out there actually are binaries. Yeah. And now that the detection methods are improving, we are gaining resolution, we are starting really to have much more planets in binaries. P-type are pretty hard to detect. We know about 30 of them. So most of the exoplanets in binaries that we know are this S-type. Yeah. And the reason why the number has increased so much in the last years is a combination, is thanks to transit surveys. So particularly TESS now, that is operating now. And with follow-up from Gaia. Yeah, when we observe a transit, so in principle we don't know the stars, the stellar fluxes are blended. We don't know if the star is actually a binary or not, but we can detect the transit. And then follow up by astrometry, mainly by Gaia, can actually tell, this star is in reality a binary. So the planet that was detected before actually is orbiting a binary star system. I give a bit this introduction on binary because I'm working now on that, but actually I will explain, most of the talk will be about exoplanets around single stars. And I will go back to these binary planets at the end if there is time. So going back to planets around single stars and back to Kepler, probably the most important result of the Kepler mission was to find that the exoplanets with sizes between Earth and Neptune are the most common ones. Yeah. And we don't have this type of planets in our solar system. So these objects naturally raise the curiosity to understand what are they made of and how do they form. If we look a bit more in detail into these occurrence rates, this is a diagram of occurrence rates, radius, orbital period, and the color is the occurrence rate. So green, high occurrence, and red, low occurrence. And here is size of Neptune at 4 radii, size of Earth. So you really see that the most common planets are planets in between these two sizes, and actually half of the sun-like stars have a planet like this. At least we are talking about orbital periods within 100 days, which is where Kepler has completeness. Farther out, we actually don't know. In 2017, something extra happened, very important, that there was the stellar parameters of the Kepler stars were predetermined because there was much improved spectroscopic measurements. And then all the planetary radii were recomputed. After doing that exercise, it was realized that the size distribution of small planets is actually bimodal. Yeah, there is a peak here about 1.3 and a peak around 2.5. And there is this depletion of exoplanets between 1.5 and 2 radii, and this is what we call the radius valley, or it's also known as radius gap. And this feature, this bimodality, this radius gap was then confirmed by many follow-up studies. So now we know that the most common type of exoplanets have this peculiar size distribution, bimodal size distribution with this radius valley. There were also follow-up work addressing the dependence with stellar mass and with orbital period. So for sun-like stars, there is a positive slope with stellar mass for the location of the radius valley, and negative with orbital period. And M-dwarfs, this is even more recent work. There is now more work going into understanding planets around M-dwarfs, as you know very well from Carmen, for example. And M-dwarfs seem to behave different. The slopes, there is no clear radius valley, actually, and so the slopes are much more flat. So all these are observables from the statistics of exoplanets that theories must be able to explain. Yeah, good theories must be able to reproduce these features. So now we're going to try to understand theoretically why this radius valley happens. How come we have this depletion of exoplanets at this radius valley? And for that, I will first introduce some concepts of planet formation. I know the audience here is very diverse, so it's important there are some concepts that will be important for the rest of the talk. Let's see if you can get a crash course on planet formation with one slide. So yeah, planets form in disks. We observe this protoplanetary disks, and we have very good images actually from ALMA. The disks are a byproduct of star formation. When the stars are forming, the molecular cloud collapsing to conserve angular momentum, there is a disk that forms. And from this material in this disk is that we have to form the planets. The disks are mainly gas, 99% gas, mainly basically hydrogen and helium. And there is 1% of solids, so dust that is accumulating, growing into larger aggregates. These solids are key to grow the planets, yeah, because the dominant paradigm of planet formation is core accretion model. And basically, the idea is that to form a planet, first we need to accumulate the solids. We need to form a solid core from these solids in the disk. What is the composition and the distribution of solids in the disk also matters. So at very close to the star, where the temperatures are hot, there can be refractory material that is solid, like silicates, but not water. But if we move further away from the disk, then we can reach low enough temperatures, approximately at 170 K in protoplanetary disks. At that temperature, water is able to condense, so we have an enhancement on the amount of solids. The surface density of solids increases by a factor of approximately 2, so we have more material to build the core of the planets. This concept is very important, the ice line, yeah, where we have the water. It's the water ice line, but it's more generally known as the ice line because it's the most important one. And also something where we know from observations is that the disk lifetimes are within 10 million years. So we have 10 million years to build our planet. To continue the idea to explain this core accretion model, one has to form this solid core by accumulating the solids. When the core is approximately 1 Earth mass, it can start to already bind a thin atmosphere. And a few Earth masses, then we can have more substantial atmosphere, 10% of the planet mass. And if we even manage to form a core of 10 Earth masses, then a process of runaway accretion of gas can happen if we have still enough gas in the disk. So if we are within this lifetime, and then we can form something very massive as Jupiter. Yeah. But so we need, when the planet is growing, it will accrete solids and gas in principle, depending on the mass of the core. And that's how we can end up with planets that have core and substantial atmosphere. There is another very important process that happens during formation, which is planet migration, and it should be illustrated by this movie, if it works. Yes. So when the protoplanet is above 1 Earth mass in a sun-like star scenario, the planet also starts to interact gravitationally with the disk and exchanges angular momentum. And this leads to an inward migration, typically. There can be a bit of outward migration, but typically the planets go to much shorter orbits than when the formation started. Yeah? So all these are very important processes that happen at the same time, and we have to model them all together when we model planet formation. Another important concept is that we refer to formation to all these processes, everything that happens as long as there is a gaseous disk. Yeah, so within 10 million years, once the disk is evolving and once the disk is dissipated, the planet will still continue evolving, will cool, will contract, the size will change, but all those processes we refer to as evolution. Yeah, formation is when there is a disk. When the disk is dissipated, we have the evolutionary processes. And going back to the radius valley, The first theoretical explanations that came to that managed to reproduce the reuse valley were actually pure evolution models. Yeah, so things happening after the formation. And the models that could reproduce that, there are two versions. One is for photo-operational, for power mass loss, but the idea is the same, is that there must be some process that removes atmosphere. So the idea is that we start with the same type of planets. After formation, we have exactly the same type of planets. So the super Earths are the first peak, and the mini-Neptunes are the second peak of the bimodal size distribution. And just by removing the atmosphere, some planets will be completely stripped off in these models, and some will manage to retain 1% of the hydrogen-helium atmosphere, and this will produces the peak of the mini-Neptunes. You can see better here. For example, here, yeah. So they manage to reproduce. On the background is what comes from observations. These models find something else. Because they assume that the cores have one unique composition, they can try different compositions. And they see that they only match the location of the valley when the underlying cores are rocky in composition. So the model it works as long as the core is rocky and always the atmosphere is hydrogen and helium. And then they get the correct location of the valley. With other compositions, they don't. So they also conclude that all these planets, the super Earth and mini-Neptunes, so the two peaks of the bimodal size distribution, originally were dry planets. This means that they must have formed inside the water iceland. And that's actually completely in contradiction with what we find with formation models. Yeah? Precisely because of the concepts that I introduced before, beyond the iceland, there is more solid material. So growing mini-Neptunes is easier. The bigger planets in the distribution, the mini-Neptunes, the second peak, it's easier beyond the iceland. And also migration is at operation at this mass range. So migration brings these water-rich planets from beyond the iceland to close in orbits. So it's from a formation point of view, there should be plenty of water-rich planets. It cannot be that the mini-Neptunes are dry, as the evolution models are predicting. And actually, when I started working on this topic, I really tried to okay, let's try to from formation to form dry planets, and let's see if we can explain the two peaks of the distribution. And we cannot, actually. There are no dry, especially at the location of the second peak at 2.5 radii. We don't get any dry mini-Neptune. We really need to have planets forming beyond the iceland. So I will show how we still manage to get the reuse valley even with water-rich planets. But I will explain a bit more what the ingredients that go into all these global formation models. Yeah. So we have, as I already introduced before, we have a gaseous disk in the model. So this is all run numeric simulations. We have a gaseous disk that is undergoing viscous accretion, is irradiated, is undergoing X-ray photoevaporation. This makes the disk evolve. We also have dust growing from micrometer size to centimeter pebbles. So we have a correlation model, and the dust, these pebbles are fragmenting also and are drifting. It's very important. The pebbles are drifting because they suffer aerodynamical gas drag. So if we have a moon mass embryo growing in that environment, it will grow by intercepting these pebbles that are drifting towards the star. It will also grow by accreting gas from the disk. So eventually we have a protoplanet with an atmosphere, and it will also undergo migration that is included in the model. This migration typically will move the planet to the disk inner edge. And after the disk is dissipated, then photoevaporation really can act on the whole atmosphere of the planet. And if the planet is low mass enough and close to a star, the atmosphere can get completely stripped off by photoevaporation. So all this is included in the model. And let's look a bit at the results that we get. Can we really reproduce the reuse valley? So to understand the results, first here I'm illustrating some formation tracks. So this is the mass of the cores. You know now what is the cores. this that accumulated all the pebbles as a function of orbital period. Yeah. So this is a formation track. It means that the planet actually starts forming here at 1 mass embryo, growing mass in this direction. So time goes in this direction. Yeah, the planets grow. And the color bar here is the ice mass fraction of the core. Yeah, the ice line initially is here. Actually, the ice line is also evolving as the disk evolves. And these planets are all formed beyond the ice line and are very water rich. This is something very peculiar in this model because there is like no intermediate compositions. So these are really illustrating some clear trends. This pattern of growth. There is a differential growth here. There is small rocky cores versus large icy cores. Yeah, and that will actually lead to the radius valley. So let's try to understand why we are having this output from formation. Why we have large icy cores versus small rocky ones. And it has to do with the pebble growth. So the pebbles, the icy pebbles are more sticky. They grow to larger sizes. This is pebble size is function of orbital, so along the disk. This jump here in all the different disk models is the ice line. So beyond the ice line, the pebbles are larger because they are more sticky. And this helps to build bigger cores because it's easier to accrete larger pebbles. They suffer more aerodynamical gas drag, so the accretion rates are higher. So we can grow bigger cores. And we can effectively grow bigger cores because also there is this concept of pebble isolation mass. There is a certain point during the growth of the planet, when it's massive enough, it creates a pressure bump beyond the orbit of the planet. And in the pressure bump, the pebbles get stuck. They cannot drift anymore, so cannot be accreted anymore by the planet. So this gives the final mass of the core. This is why this gets halted here, the core growth, because they reach isolation mass. And isolation mass also increases when we go to the cooler regions of the disk. This is why we effectively can grow bigger icy cores than rocky. Yeah, so these two effects are at play. And when we launch a population, that means doing hundreds of simulations, barring the initial conditions in the disk, then this pattern is actually still visible in that we have this bimodal core mass distribution, rocky versus small rocky versus big icy ones. If we plot it in terms of sizes of the core, then it's when it gets really interesting because we really reproduce the bimodal size distribution. Yeah. So at the end, this dichotomy during the growth given by the pebble accretion is providing these hints of giving to reproduce the radius value. This is not the full story, though. It's more complex because, as I said, the planets also accreted gas. Yeah, this is only looking at the solid cores. So in reality, the full size of the planet taking into account the atmosphere, this gets more smeared out. So actually, this bimodality is hidden at the time of this dispersal below these gaseous atmospheres. But then is when photoevaporation is important because photoevaporation, of course, occurs after this dissipates. And there are also other processes to take into account to lose mass. For example, there will be a phase of giant impacts. So we have some simple prescription to remove gas by giant impacts. And then we kind of recover again this bimodality in the size distribution, the location of the radius valley. Yeah. So both things are important. Like formation is setting up the core size distribution in the correct location with two different compositions. That's different from the pure evolution models because formation tells us that there are two key compositions, ices and rocks. We cannot just forget about that. That's what formation tells us. And then we need really the evolution to remove the atmospheres and recover this radius valley. Just to highlight that this was the first time in the study that we reproduced the radius valley from global formation and evolution models, predicting that mini-Neptunes should be water worlds, contrary to what was said by evolution that these planets should be dry, and this should be very water-rich planets, water worlds. We have also, so we have also expanded the model for different stellar types, particularly, as I said before, there's a lot of research going into M-dwarfs. So it's interesting to understand these trends for different stars. And yeah, just here another way to see all the ingredients that are in the model. So it's many processes that do information, but also the evolution to remove the atmosphere. And actually, we are using state-of-the-art at the end, state-of-the-art interior structure models to compute the structure of the planet to get good planetary radii. What do we find when we repeat this exercise for different stellar masses? So here is the sun-like case, sun-like star case, one solar mass. This is mass and radius of the form of the synthetic planets, and the color bar is the water mass fraction of the planets. Again, one sees clearly this dichotomy of rocky versus water worlds pretty much everywhere. There are some exceptions, but yeah. And one thing that also probably calls your attention is when we look at lower stellar masses, so when we go to M-dwarfs here, these water worlds actually, here the radius value was very clear. Yeah, you can actually, when you project to the radius axis, you can see that there is a clear valley here, clear gap. But this disappears when we move towards M-dwarfs, yeah, because the water planets, the water-rich planets that form beyond the ice line, are now arriving. We are looking at short orbital periods always. Now we have smaller ones that reach short orbital periods, and then there is no clear valley. Yeah, there starts to be this overlap in radius between the rocky and the water. And why does that happen? It has to do with the migration. The planet migration, actually, when the stellar mass, this is very well known in migration, in type 1 migration. When the stellar mass decreases, then planets can migrate at lower planet mass towards the inner regions. It's not anymore the 1 Earth mass threshold, it goes down. So smaller icy planets can reach the inner parts of the disk now and smear out the radius valley. So our model is also predicting, because of this migration effect, that the minimum mass of these water worlds should go down. This is actually observed. This is a recent paper. And it was also reported by Luque and Palais. It was a famous paper 2 years ago. And we are actually getting good agreement with the minimum mass of these water worlds from our simulations. Another thing to look at, I mentioned at the beginning, is the slope in the radius versus stellar mass, the slope for the location of the radius valley. This is what we analyze here. This is planet radius versus stellar mass. The color is, again, the water mass fraction in the planet. And these lines here come from analysis of observed exoplanets, all this works. And the blue is what we get from the analysis of our synthetic planets. And we get, so these other slopes cover different regimes in stellar mass, and we get quite good overlap with all the regimes, although of course here there is no really clear valley, and it's more dictated by this. This is the slope that we get with stellar mass for the radius valley. Yeah, in this part, you see that, again, how the radius valley gets filled, it fades towards M-dwarfs, are also found by observations. And we are finding a very depleted valley, very empty towards F-type stars, which is also reported. For the orbital period, we find good agreement, like a negative slope for sun-like stars, and because there is no clear radius valley, it's really flat for M-dwarfs, and this was not predicted before by pure evolution models. Okay, so just to summarize all this radius valley, I know it's a lot of theory and a lot of results. So just to take some home message. With pebble-based formation and evolution models, we reproduced the radius valley and predict that mini-Neptunes are water worlds. We reproduced the slope of the radius valley with stellar mass, with that functionality. I didn't have time to talk about that, but also there is an effect of the water. There is, if the planets are warm enough, if the equilibrium temperatures are above 400 K, then the water that was accreted as ices actually will be in form of steam because the planets are hot. And this also puffs up and helps to have a deeper radius valley, puffs up the planetary radius. we find that the radius valley phase towards M-dwarfs, as I just said, and the minimum mass of water worlds is in agreement with observations, and also the radius period slope flattens for M planets. And if you want to use this synthetic data, actually you can download it from here. Going back now to binaries, and then I close. It's just a few more slides. The field of planets in binaries is really now starting to launch. And there are only a few studies that have addressed the problem of the radius valley for planets in binaries. We are talking about S-type because it's for the planets in binaries that we can do some statistics. The others are too few for P-type. There are just these two works, so from the same group, reporting on the existence or not of the radius valley. The newest results are showing that if we go to really close binaries, then the population of mini-Neptunes, the second peak, gets depleted. It's this blue curve, sorry, is the distribution of S-type planet sizes. Yeah, so there is a suppression of mini-Neptunes apparently for binary separations closer than 100 U. For larger than 300 U, they say that the radius valley is shifting in location. But just to focus on that, again, can we understand this from a theoretical point of view? And to really try to understand it theoretically, we need to develop these global models for S-type planets. And this is my main project now with the grant that I have. And this is the work we are doing with Ariana, my PhD student in Geneva. So we are adapting this global formation and evolution model to the presence of a stellar companion. What we included already is this. The biggest effect is the truncation. There is a tidal truncation of the disk, so there is less material to form our planets. And there is also, of course, the perturbation, the gravitational perturbation from the secondary affecting all the growth process, which the closer the binaries are, the more detrimental the effect. We have run some simulations, initial simulations with pebble accretion again, and we really see that planet formation gets suppressed when we reduce the binary separation. This is planet mass as a function of time for different planet locations. And the curves, yeah, this is so the planet mass, how the planet is growing for the different binary separations. In the case of single star, that is here below this violet curve, in this case, we were getting a Jupiter, super Jupiter mass planet, a gas giant. But if we start to reduce, then, for example, if the binary separation is 50 AU, we get only an Earth because of this shut off of the pebble flux. There is much less solids to form the cores of the planets. So the definite answer about the radius valley is still open because we are still working on concluding these model developments to start to launch the populations. So yeah, this will be work to come. The message to retain is that the closer the stars and the farther the planet is in the disk, the stronger is the suppression of planet formation. This is what we are seeing with these simulations. And finally, so as I said, there are some results for S-type planets coming from Kepler. But also TESS, of course, is a survey that is going on now, and for brighter stars, so the follow-up is much easier. There are plenty of S-type planets being discovered by TESS, and I'm leading a program in CHEOPS, a GTO program, to readdress this question of the radius valley for S-type planets. So we are observing TESS planet candidates with CHEOPS, refining the transit parameters, identifying which of the two stars is really the host. That's a whole other topic to discuss. And we are getting also nice results, but yeah, once the program is finished in 1 or 2 years, we can then have really results to show. But it's important, there will be hundreds or not, if not thousands of S-type planets in the future, also with Plato. Plato will be launched in 2 years. I'm also leading efforts to have a working group for S-type planets in Plato. So if you're interested in that topic, you want to join this working group, please contact me. And there's a lot of science to do for planets in binaries. Thank you for your attention.
Julia, very nice talk. One question is it even more enhanced with if you talk about planetary densities?
If it's
than
enhanced.
radii?
For the density.
Yes.
Yes, there is a density value actually. I didn't want to also go into that. I don't know if I have some.
Okay. It's more enhanced than.
It's more enhanced, and it's for all stellar. With these models, we find that there is a density value for all spectral types. Yes.
So, are there any questions?
I have a question. So while I could follow the literature on this, but I recall that there was a problem with the pebble growth and the grain size growth. So when you go from micron or millimeter size particles to over centimeter size particles, the models were showing that the particles would destroy what they would collide, and then somehow you needed to build at least one boulder 10-meter size to start more efficient. So how has this been solved, or is? Yeah, it's
a very good question. It's a topic that on itself it's a very active area of research, how to form the planetary seeds, so the planetesimals. And it's true, the pebbles are drifting. Small planetesimals are also drifting and colliding, but we also lose them because of the drift. So it's hard to accumulate. But since already several years, the answer seems to be streaming instability. So there is a process called streaming instability that helps to accumulate in bumps these solids and produce 100-kilometer size planetesimals. So that's the short answer. It's through streaming instability. And that produces the planetary seeds. Yes. Then to grow to one moon mass is not so complicated, actually. That's understood. The bottleneck was the planetesimal formation. Yeah. But there's still a lot of debate going on in which regions are the preferential ones. And
I get that in your clamps, what you call, you have lower velocities, relative velocity with the particles, and then the collisions are not so destructive.
So the simulations we do don't include all that, because these global models use simplified models, so typically 1D models or some prescription for migration, for example. So we take the results of very detailed models for the initial conditions or to mimic the processes. So.
And more questions?
I was wondering what this, do you expect the Venturini effect will be visible in the reduced value if you consider also stellar rotation or metallicity, or is that something that expect to affect?
That's a great question. About stellar rotation, honestly, I don't know. And for the metallicity, there are no clear trends regarding metallicity. In principle, when you have more metallic disks, you form bigger cores because you have more solids to form the cores. So yeah, in this picture, it could enhance the mini-Neptune formation, maybe also thinking now with the binaries. But there are no clear trends observed with metallicity.
Actually, a little bit connected to what Alexandra, not so much metallicity, but I guess the CO ratio must affect how much water you have in the mix, because otherwise a lot of oxygen.
Yes.
So is there any influence, impact on how people look at the relation between the stellar abundances and
yes, so this jump of 2 at the water ice line is, strictly speaking, is for solar composition. So there is a distribution in reality, but the change is not that big. So this jump, there are some, I don't recall exactly the numbers, but it's not such a big effect for the surface density of water. C2O, it's very complicated something to look into, actually. It's very difficult to link it with the formation.
I was thinking a question that stems from my complete ignorance of incompetence of experiments. So when one tries to detect them, are there observational biases? Like, I mean, is it to detect bigger ones?
Of course.
I don't know. That in principle they can be taken or have to be taken into account when one wants the population.
Yes, yes, that's a great question. Yeah, of course there are already like plots like this size orbital period. There are many observational biases. Like with transit method, we tend to observe big planets that are very close to a star. Those are the easiest to detect, but the biggest planets actually are the less frequent ones. So one has to correct for. So people do observations correct for all the biases coming from sensitivity studies of the, or knowing the instrument, knowing the observational strategy. And when we do simulations, if you want to compare really the precise distributions, you need to impose also some biases, yes. Particularly if you're comparing to specific survey, you have to cut also your population. This is why, for example, we in the results I was showing, it's all for orbital periods below 100 days, because Kepler was really observing at that period range. So you have to do some cuts. It's easier to do them on the synthetic planets than to do it from the observations, actually.
Yeah, thanks, Julia. You mentioned these two main mechanisms that have been proposed to explain the radius valley, like photo evaporation and core powered mass loss. Can your model say which of those scenarios is more likely? Are they both in your simulations?
Yes, also. I highlight photo evaporation because that's the main one, actually. And in somehow we include core power mass loss because we include the heating coming from the formation. So it's there in the interior structure of the planet, but we don't see any effect, honestly, coming from that. So it's not very clear what luminosities they are using in the core power mass loss models. Yes.
One more. You mentioned that you are studying mostly S-type binaries, let's say planets, S-type planets, because there's still no statistics on P-type, let's say. What can you say something about what your feeling might be? Is what do you think about
for the P-type?
Yeah.
Yeah, maybe I can show again one of the first plots. This one. So these diamonds are the P-type, actually, and you already see something very clear, and they are much farther out than the others. And that's because in this case, the disk is truncated inwards. There is an inner cavity, and then you cannot, and there's also a dynamical instability region in that location. So there cannot be planets close to the two stars.
Then you don't expect rocky planets with no, let's say, gas poor planets.
It's not that easy. It's not that easy because the fact that you have a cavity doesn't mean that you only have the ice line. So the cavity is inside. You still have dry regions in the disk. It's just that for habitability, for example, it's a very interesting aspect because if there are P-type planets that we know there are, but if there are a lot, which we don't know, they tend to be in more temperate regions. Yeah.
This is interesting to science
but it's
fiction.
not known if yeah exactly. I mean, these things it's worth to mention. These things were pure science fiction 20 years ago, and now these planets are real.
Yeah, very general question. So would you say that for most of the M-dwarf planets that are close in with these multi-planet systems, are they more likely to be water worlds,
Yes.
right? In
Yes.
composition. There's not much mass in the dry zone, let's say.
You can have also. No, I have to go back.
I mean, you can form some terrestrial, but the area is so small that you will not have material to form purely terrestrial planets.
The ones that are the biggest size, that the mini-Neptune size, should be water worlds. Yes.
But even the small, I think that.
And the small, we can look again at the plot because that's also like. So you can have, above 1, you can still. Below 1, no. There should be dry. There should be rocky. There can be some exceptions, but above 1, at least these models predict that you can perfectly have water worlds of 1 Earth mass around M-dwarfs.
And you get your planets locked into these multi-planet systems with resonances and.
In these models, there was only 1 embryo per disk because there was no gravitational interaction between the different embryos. In the model that we're developing now with my student, it comes from Bern and it has all this. But in these results, no, we only have 1 planet. And that's why they get stranded at the disk inner edge. But of course, when you include the multi-planet systems with the gravitational interactions, they get, because of migration, they get trapped in resonances. And you have resonant chains. I mean, and that some have been observed even with CHEOPS.
Yeah.
Yes, you know.
Are there more questions? We have still a lot of time. Thank you. And no? Okay, then thank you so much again.
Thank you.
Pizza will be served outside in 10 minutes. As always.